First of all, make sure you've read through the problem and understand what it's saying. A couple little details, just kind of an aside here. If you're wondering what a metacomp is, it's what came to my mind this morning when I wrote it just for fun. I made up that unit, okay? Because otherwise we'd be dealing, if we were talking about real like electrical circuits or computer processors or something like that, we'd probably be talking about millions of computations per millisecond. And that just ends up being too big of numbers. I didn't want to mess with that right now. All right, so we have this type of circuit. Notice it doubles every year. Its performance doubles every year. And we know that the performance right now is 20, and we want to know what it's going to be in 15 years. In order to figure this out, you're going to want to use your notes. Now, the notes that we took on this is this. Now, I'm not going to leave this up there long enough for you to write it all down because you should already have it written down. But I'm trying to bring this back. Find this in your notes and use it as we go forward here. So we're going to use this equation to write the equation for this particular problem. So in this particular one, we start with this a of t over here. When you go to write the equation for this problem then, just write a of t equals. And of course be doing this as we go, be doing it along with me here, so everybody should be writing this down as we do it. From here, we now need to get in the p value. Now notice what p represents. It represents the starting amount. Because p, in case you're interested, why is it p? Because p stands for principal, which is another word that represents starting amount. So what is our starting amount in this particular problem? 20, absolutely. So I know a of t equals 20 times something. So the next thing that I put in there is the r, which is rate of change. So what am I multiplying it by every year in this case? 2, absolutely. So I know it's going to end up being 2 to the t. Now in this particular problem though, I actually know what t is. What is t? 15, yeah, because we're looking to see what it is after 15 years. Now notice a little detail here though, and this is one of those little details that started to be overlooked, and so I want to make it a point of emphasis here for you. A lot of people are losing this part of it. The whole idea of this function notation where we have a letter and then the parentheses is it's saying the value of a when t is 15. We need to include that value. When you plug the 15 in up here in the exponent, you plug it in for t everywhere, including there inside those parentheses. All right, having written the equation, we now need to figure out what it equals. Now, when figuring out what this equals, am I going to be doing the 20 times the 2 first, or am I going to do the 2 to the power of 15 first? 2 to the power of 15. Yeah, 2 to the power of 15 first. So, and the whole idea is because it's order of operations. We got to do exponents before multiplication. So, do that 2 to the power of 15th on your calculator. Get that number. When you did the 2 to the 15th, you hopefully found that it was 32,768. So we now need to do that number times the 20. Now, as I'm doing the work, notice how I'm showing the work though. That a to the 15th that I wrote first, I carry it down. I keep writing that same a to the 15th every step. We're organizing our thoughts. We're organizing our work here so that it clearly communicates what we're doing. It's also going to make you more efficient and more accurate in your algebra. When we do that 20 times the 32,000 number, we end up with 655,360 for our answer. So that's all the algebra. This is exactly what I expect your algebra to look like. Yes, I need to see all of those steps. Just to make sure that we get what that's talking about then, that means that this completes 655,360 metacomps per millisecond. Notice in this problem, I think probably one or two of you were going, wait, milliseconds? How many milliseconds are in a year? Notice that since it's part of the units, it's part of just the measurement of the speed of the circuit, we don't have to figure that out. The milliseconds and the years here are talking about different things and doing different things. In this problem then, we're going to be looking at a population of rabbits. Now, this would definitely be an exploding population for sure, because we're looking at starting at 400 rabbits. It's growing to be 4 times as large every month, and we want to know how many rabbits will be in the area after a year. So again, we got to start by writing our general equation. Because it is talking about multiplying our values by some number. We still use this equation. We're still going to make it an exponential. Remember, an exponential is anything where we raise it to that power there. So that's what tells you to use this again, anytime you're multiplying the last value by something. All right, so if I go and plug this in then, I again start with my a of t. Now in this problem, what is the value of t? Well, one question that sometimes people have, is it going to be 1 or is it going to be 12? The way that you know is notice it's going to be 4 times as large every month. So then we're going with the month number, so it's going to be the 12. Nice. Okay, next up, the p-value. What is the value of p in this problem?
400.
Absolutely, it is 400. So why 400? Because p is the starting value. And so we start with 400. Now the r. What is the r in this problem? 4, absolutely, because the population has been growing to be 4 times as large. Now it's going to be to the power of t. Now in this problem, I already figured out what t was, right? Whatever I plug in for t here has to be the same that I plug in for t here. So it's going to be 4 to the 12th. Now that we've written our equation, now you can go ahead and figure out what it equals. So go ahead and do that calculation, figure out what does this give us. First up in that calculation, again, do the exponential. 4 to the power 12 ends up equaling 16 million and change. Okay, so then I take that whole number and I multiply it now by 400. Your final answer here should be 710,886,400 rabbits. Yeah. I think that would qualify as an exploding population. Now, if this actually happened, that would be a whole lot of rabbits, right? So just a little bit of insight about these exponential models. When we use these kinds of exponential models, what you'll often find is, especially when you're dealing with something like this that deals with biology, the model will work really well for a while. But if there were really 6 billion rabbits in this area, they would quickly eat themselves out of all food sources, right? It would all of a sudden stop working as well. So be aware that these models can be very good representations, but when we start applying them in the real world, you might see some cases where it works well and then it stops being a good representation. Oftentimes math works like that, as we start saying, okay, it's correct until this starts happening, and then it's going to modify some. So just be aware that that often happens with these. All right, and we're now going to go do one last problem for today. This is following directly up on what we did yesterday. Please write down and solve this to make sure you got yesterday's work down. So in terms of showing the work as detailed as we can, I expect to see on every step, what are you doing to both sides of the equation? And in this case, notice I chose to subtract the 3x squared from both sides. 2 things on this. 1, make sure you write the x squared with it. I see some people just write minus 3 minus 3. But 3 is not the same as 3x squared. We got to do it correctly. The other thing is, make sure you actually write it under both sides here. We can't just put it under one, because then we run the risk of forgetting about it on the other side. So we write what are we doing to both sides, then we write what does that give us. Then I do the next step, and I show what I'm doing to both sides there. Then, what does that give us? And then again, what are we going to do to both sides? You write it out super clear, and then write what that gives us. You're always showing as much work as possible on these. By showing that work, you actually make yourself much more accurate, and you build up a better and deeper understanding of algebra and why the way it works the way it does. Otherwise, it's easy to forget. Okay, to finish out this problem, picking up from what we did yesterday, we got x squared equals 49. I need to get rid of the squared, so I'm going to square root both sides. What do we need to include when we take the square root of both sides?
Minus.
When we take the square root, we include the plus or minus. And so, x ends up equaling a 7 and a negative 7 here. Yes, you need both answers.